Welcome to this video on our NeurIPS 2024 oral presentation on optimal parallelization of boosting, which is joint work with my postdoc, Arthur de Cunha, and my PhD student, Michael Müller-Høsgaard. So Arthur's made these slides, so thanks a lot to him for preparing them. And I guess in this talk, I'll just go over our conference presentation in a slightly extended edition. And let me also add that at the time of this recording, both Arthur and Michael are looking for jobs. So if you want some really excellent postdocs, please do contact them. Okay, so optimal parallelization of boosting. Let's get to it. So what is the result in this work, and what are we doing? So what we're looking at is binary classification problems. So in particular, just to introduce some notation, we'll be working with an input domain X and a data distribution over it. So for instance, the input domain could be images of cats and dogs to keep it simple. And working with the label space, so a set of labels here, the set of labels as cardinal is just two, so we're doing binary classification. So in this example, the label space could just be the two different labels, cats and dogs. What we always also have is a target concept that we're trying to learn, which is just a mapping from the input domain to the label space. So basically think of C as assigning the correct labels to each of the inputs of the input domain, right? So mapping every picture to whether it's a cat or a dog on the picture. Okay. So a little bit more abstractly, we'll be using notation x1, x2, x3 to denote the input element from the input domain, and we will be just using the labels -1 and 1 for simplicity. So this target function now is just a mapping from this input domain x to -1, 1. And the way we're going to visualize it, if we had such a training data set, for instance, of 5 training items, we're just going to view it, at least in these slides, as a vector here, where we write in every entry whether the label is +1 or -1, so whether the target concept assigns a plus or a minus. Right, so the first entry here is really the label assigned to the first training item x1, in this case +1, and so on. This is just notation. Good. So the goal of what we're trying to do now is to, I guess, construct a so-called strong learner, right? So if we look at the entire input domain, our concept is assigning labels to the entire input domain, but we don't know what they are, right? But we'd like to try and learn this concept C. And what we have available, again, is training data, M items, M training data points, where each data point is sampled independently from some unknown data distribution D. So we might get 8 examples where we from this input domain. And then what we see is basically the target concepts assignment of labels to these data points. Right? So we write it like this: C projected onto S is just the labels that C assigns to this training data set S. Right? So it assigns pluses and minuses to these data points x1 up to x8 in this example. Okay. And what we're then going to do is we're going to try and run some kind of learning algorithm on this labeled training data set to produce a hypothesis H. And this hypothesis H, we can now look at, or classifier H, we can look at how does it perform on this training data set. Right, so presumably we were trying to find some hypothesis or classifier that performs well, that labels most of the data correctly. And then what we're trying to hope is that this good performance on the training data, so meaning we classify most things correctly here, also with high probability means that if I apply this function H, the classifier I trained, also on the full input domain, it's going to agree with the target concept almost everywhere. So here I'm using red squares to denote a misclassification of a data point and green squares to denote a correct classification of a data point. Okay, so we wanted to basically correctly classify most of the input domain. So if we wanted to be a little bit more formal, what we're really after is a so-called strong learner, meaning that for any target accuracy, a precision epsilon, we want it to be the case that if I have enough training data, so I have some M of epsilon many samples from this data distribution, and I see the labels of my training data, so I see the target concept evaluated on this training data set, then I want it to be the case that with high probability, my strong learner, my learning algorithm, produces a classifier H that approximates C well on the entire domain, not just on the training data set, where we mean that the error of this classifier H, namely the probability over a fresh data point from the same distribution as the training data, the probability that I misclassify this data point, that my prediction h of x is not equal to z of x, the true label of this data point, is at most epsilon. Right, so this is the overall goal. We want to build such a strong learner. But what we want to start from is something much weaker, namely what we call a weak learner. So what is a weak learner? So again, if I have a training data set S, I see the labels here. So what the target concept assigns to each of these data points. Maybe I don't have a learning algorithm available that correctly classifies almost all of this training data. Maybe I have a so-called weak learner. So a weak learner now is something that then on a training data set and the corresponding labels computes a classifier H, so that if I evaluate H on this training data set, it's going to be correct on 50% of the data plus some advantage gamma, right? So it's a little bit better than guessing when we're in the binary classification case, right? 50% accuracy is the best is kind of random guessing, and you're a little bit better than that. So you have some advantage gamma over random guessing. So we call this a gamma weak learner, right? So it correctly classifies all these green points a little bit more than half of the training data. And what we want is that actually this weak learning algorithm, we want it to be a little bit stronger than just being able to classify the training data with a little bit more than 50% accuracy. We want it to be the case that for any weighing of the training data, so think of D as a distribution over the training data now, not a data distribution over the input domain, but a weighing of my training data. For any weighing of this training data set, for instance, the uniform weighing, I should be able to run this weak learning algorithm and find something that's a little bit better than guessing on this weighing. But I want it to be the case also for non-uniform weighings of my training data, right? So if I have like a distribution like the one here, I want it to be the case that I can invoke this weak learning algorithm with this distribution and the training data set, and it will produce something for me whose accuracy is a little bit more than 50%. It's 50% plus gamma on this weighted version of the training data, right? So if I basically sum up the probability mass assigned to all the data points that it correctly classifies, this area or probability mass should be at least 50% plus gamma. Then I have a gamma weak learner. So this is standard definition in the literature, and we can also do it a little bit more formally here. An algorithm is a gamma weak learner that we just from here on denote by a W sub gamma. It's an algorithm that, given a training data set S and the true labels assigned to them by the target concept, and it also takes as input a distribution or weighing of this training data. So it gets a D. And what it does then is returns a classifier H that approximates this target concept a bit better than a random guessing on the training data when we weigh it according to this distribution D, meaning that if I sample one of the training data points according to this distribution D, so remember the distribution is just over the training data. So if I sample a data point according to this distribution, then the chance that this classifier that I produce mispredicts the label is at most a half minus gamma. Right, so this is the error is at most a half minus gamma, meaning the accuracy is at least a half plus gamma. Okay. So this is a weak learner, right? So we want something that is a little bit better than guessing on any weighing of the training data. Right, and now the classic algorithm for taking such a weak learner and constructing from it a so-called strong learner, one that can get arbitrarily high accuracy given enough training data, is AdaBoost. Right, so just a really quick recap of what AdaBoost does. So you get the training data set, and what you do in the first kind of round of boosting is you just assign a uniform weight on all the training data. Right, so then you feed this uniform weighing on the training data into a gamma weak learner, and this will produce some hypothesis H1 or classifier H1, whose accuracy is a little bit better than 50% on the uniform weighing of the training data. Right, and now AdaBoost is doing these multiplicative weight updates, meaning that it's going to increase the weight or probability mass assigned to data points that H1 misclassifies, and it's going to reduce the weight on data points that H1 correctly classifies. And so we get this new weighing here. And now the idea is that you now, from this second distribution D2, you now feed it back into the weak learner to find something again that's a little bit better than chance on this weighted version of the data set. And so this gives you a hypothesis classifier H2, whose accuracy on this reweighing D2 is at least 50% plus gamma. And again, you increase weights of misclassified data points, you decrease the weight of correctly classified data points to obtain a distribution D3. And Then you feed D3 into the weak learner again. It's going to compute a hypothesis H3, whose error is at most half minus gamma, so its accuracy is a half plus gamma under this reweight version of the training data set. And you repeat this for a bunch of iterations, always up and down scaling the weights, increasing weights of misclassified points, decreasing weights of correctly classified points. And after sufficiently many rounds, you're going to aggregate all these classifiers that you trained by doing a majority vote amongst them. Maybe it's a weighted majority vote. AdaBoost is a weighted majority vote, but in general, you're just going to do some kind of voting amongst these classifiers. Right? In the simplest case, you're just going to do just going to ask all of them, what do you think the label of this data point should be? And that's the prediction that you're going with. Right? So the prediction on a data point X is you evaluate all the hypotheses, you look at their prediction, and you go with the majority. And for labels minus ones and ones, this is the same as just taking the sign of the sum of their predictions. Okay, so this is how AdaBoost works at its core. Okay. Now, boosting, I guess, is one of the most successful theory ideas that also have turned into very practical algorithms. And state of the art in practice are some more modern versions of boosting called gradient boosters, typically, in particular, there's XGBoost and LightGBM, super efficient implementations of so-called gradient boosting. Here, the learning algorithm, the so-called weak learner, the algorithm that we're running at the bottom of things, the one that we're using in every round of boosting, is typically something like a low to medium depth decision tree or regression tree. And these boosting algorithms, they're often part of the winning solutions in calculus competitions, in particular when it's like kind of small or data sets or tabular data, like even very big data sets that are tabular. This is often a very important ingredient in the best performing solutions. So, but unfortunately, it has some quite significant drawbacks. Right. In particular, if you run these gradient boosters, it often takes, at least on large data sets, something like thousands of iterations to get the best possible accuracy or performance out of these boosting algorithms. And the real issue with this is that the algorithms are super sequential, right? Even if you had thousands of computers available, there's just no way for you to parallelize the training of each of these little regression and decision trees. Basically, because as you solve the AdaBoost, you first train one classifier, then you update the weights that you put on your data, depending on the first classifier, and then you can start training the second one. So if you don't know which one to train, you cannot really parallelize this. And the same goes for these gradient boosters. They repeatedly change the labels that you're trying to fit based on previously trained decision or regression trees. Right, so there's really no obvious way to parallelize these algorithms in terms of the number of iterations that they're doing, which makes it infeasible for really large data sets or maybe very expensive base learning algorithms. Right, you don't have time to wait. You have to just multiply the time for one training iteration by, say, 1,000. You cannot just distribute this to many machines. So this is what we're looking at here in this work. We're looking at parallelizing boosting. So what can be done to parallelize the training of boosting algorithms, right? So we're going to look at it in a formal framework of what we really mean by parallelizing boosting. And then we're going to mention here also some previous works on this topic. So what we consider here in terms of what we want to parallelize is really the training phase of boosting. Right? Because typically we think of training one of these classifiers as more expensive than inference. Right? It's faster to evaluate one of these hypotheses than it is to train them. Okay, so the algorithms we try to consider, we say in general that a boosting algorithm is parallel if it does the following, right? So it gets in a training data set and the labels, and it has access to a weak learner. So it's the same classic setup of we have a weak learner, we want to construct from it a so-called strong learner, something that performs really well. Now we say a boosting algorithm has parallel complexity, or it runs for p sequential rounds if it has an outer loop that you have p phases of training, of p steps of training. And each of these iterations, you parallelly train a whole lot of classifiers, right? So you have T is now the number of classifiers that you're allowed to train in one round. So think of it as you have T machines, you can let all of them train a classifier. And training classifier in this setup, by this formal definition, means that you query the weak learner with the distribution, right? That's the training phase. You feed the weak learner distribution, and it's going to train for you some kind of classifier H that performs well on this distribution. So in our setup, right, we have P rounds. In each of these P rounds, you can query a weak learner with T different distributions, and in parallel, you'll get back a classifier whose error is at most a half minus gamma for each of these T distributions, right? Now, the idea is in general, such a boosting algorithm then do something with these hypotheses that it has found. And at the end of these P rounds of training, you have to output a classifier whose, say, generalization error is around the same as AdaBoost, right? You want the same quality of your predictions as what AdaBoost would give you with the same amount of training data. And if you look at classic generalization results, best known generalization bounds for AdaBoost says that if the weak learner, the hypotheses it's producing, or these classifiers it's producing, if they come from a hypothesis set of VC dimension D, then the generalization error should be something like D over gamma squared. Gamma was the advantage of the weak learner, times the size of the training data set, right? This is basically what AdaBoost gives you. And we want to look at boosting algorithms that gets the same accuracy, and we're aiming for doing it in P rounds, right? And also just be aware that in one of these parallel rounds of boosting, the distributions that you're going to ask to the weak learner, they're allowed to depend on all these hypotheses or classifiers that you already gathered. But you don't know the future, right? You don't know what are the hypotheses or classifiers I'm going to get in the next couple of rounds. So you kind of have to query in parallel, and then you can use the information you gain to define new distributions for the next round. So these are the class of boosting algorithms we will be considering. This is what we mean by parallel boosting. Right. So maybe just to recap some of the known algorithms, if you look at AdaBoost that we sketched before, what is known about AdaBoost is if you want to get the optimal generalization error, you have to run AdaBoost for around a log of the trained dataset size over gamma squared rounds. And in every round, you just train one classifier, one weak learner. So there's no parallelism at all here. Okay. Now, the first work to consider this in the setup with a weak learner using a hypothesis of VC dimension D was in previous work together with Amin Kabachi and myself, where we gave a one-round boosting algorithm. So it has only a single round, and the number of queries you ask in parallel here was quite large. It's exponential in the VC dimension D times log M. M here is the size of the training data set S over gamma squared. Right, so you can kind of trade off these many sequential rounds. You can turn into just a single round by doing exponentially many queries in parallel. Okay. Let me also maybe remark that there's also been previous work by Long and Sevedio that studied boosting in this parallel setup, but they assume some kind of restrictions on what type of query distributions your weak learner is allowed to you're allowed to ask your weak learner for. And this restriction that they imposed actually meant that no parallelization was possible. They proved lower bounds saying you have to do log m over gamma squared rounds like AdaBoost if you want any non-trivial error guarantee. But as our upper bound shows in this previous work, you can actually, if you define distributions that kind of circumvent their assumptions, you can actually do something in one round. But it is possible to get good accuracy in one round if you do these exponentially many parallel queries to the weak learner. So you train exponentially many hypotheses or classifiers in parallel. Okay. In that work, we also proved some lower bounds, saying that if you want to parallelize, there has to be some kind of exponential growth in the amount of total work, like there is here. But the lower bound didn't match that upper bound we had. Then there was follow-up work by Liu, Wu, and Yang, also in 2024, that gave a trade-off basically between AdaBoost and the one-round algorithm. And it's basically saying, so if you look at the number of rounds P, log m over gamma squared is the performance that AdaBoost has. So we have this parameter R. If I want to cut down the number of rounds by a factor R, then the number of weak learners that I'm going to train, or the number of classifiers I'm training in every round, grows. You can do it with exponential in D times R squared many parallel trainings of classifiers. Right, so saving a factor r costs you an r squared in exponential multiplied with a d. Okay. They also improved the lower bounds from the first work there by Kabasi and myself. But there remained a gap between this upper and lower bound that still wasn't understood what is the right trade-off. And this work closes this gap, and we actually make progress in both frontiers. We both strengthen the lower bounds from previous works, and we improve the upper bounds. I'd say in many ways, the lower bounds is a modification of the work by Lu, Wu, and Yang, just a bit more careful analysis. And the algorithmic upper bound, I guess you could also say, is kind of based on the same idea as their work, but again, with a better analysis. Okay. So what is kind of the key step in this algorithm? Okay, so remember that in boosting, typically something like AdaBoost, right? You have all these rounds where you have a weighing on the training data set. So you have a distribution D over your training data. What you could do is you could try and use a subsampling as part of it. So what do we mean here? So if I have one of these distributions, I could try to draw a random sample from this distribution, this weighing of my training data. So let me draw some n samples. The training data set size is m, n is a different parameter. So you draw some samples from this weighted distribution on your training data, gives you a subsample Q. You have some labels there. You know what the target concept predicts on these. And now what you could do is you could try to use your weak learner on the subsample using the uniform distribution on the subsample. This weak learner will give you something whose error is at most a half minus gamma on the subsample. So this is just using the weak learner on a random subsample. Now, what we could maybe hope for is that training on the subsample also gives me something that is good under the weighing D, right? So I don't have to train on the full training data set. I could maybe train on just the subsample, right? So I might still get something whose accuracy is something, or its error is at most a half minus something like gamma still. That's maybe plausible, right? So the main kind of thing we need to understand in this work is how does the performance on such a subsample, I guess, generalize to the whole sample when we have this weighing D on the training data. Okay, so if we can understand this, then one kind of key step in the algorithm is a kind of bagging step. So what we're going to do, which is also similar to one of the previous works, is we're not going to draw just one sample. When I have one of these weighings while I'm doing boosting, I'm not going to draw just one sample from this distribution. I'm going to draw a lot of samples. Like say in this picture, I'm going to draw 3 different samples, all from this distribution. And then I could run my weak learner on all these samples, right? So that's going to give me a bunch of classifiers, 3 classifiers in this example. And I'm not going to do it 3 times. I'm going to do it many times. I'm going to do it T times in particular. T is this budget that I have per every round. How much am I going to train in every round? So I'm going to sample from a distribution D many, 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 many times, draw these little subsamples, train on all of them in parallel. And then I want to somehow use this, let's call it a bag of hypotheses. I'm going to use it now to kind of perform multiple steps of boosting, right? So I train on all these subsamples in parallel, and now I want to argue that these hypotheses that I get out of this are kind of useful for doing multiple steps of boosting. So I don't have to train for another couple of rounds. So let's see here. So how does this work? So the idea is to say, okay, I know I have this gamma weak learner, right? So I have my learning algorithm always gives me something whose error is at most a half minus gamma. I would like to say that when I do these subsamplings, let's say I'm okay with finding a classifier whose error is at most a half minus gamma half, right? So it's still like a gamma half weak learner instead of a gamma weak learner. So that's kind of okay for me. So the main idea is we have this kind of procedure that we call check bag. So I have a set of hypotheses, H1 say, that I obtained this bag of hypotheses by sampling many, 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 many times from the distribution D1. I put all these hypotheses or classifiers that I train into a bag. And then I have this procedure that will check the bag. So basically it's gonna look through all of these many classifiers. I'm gonna check each of them. How well does it perform on the distribution D1, right? So they were trained on subsamples. I'm going to check it. How do they perform on the full distribution, right? So note there's no training involved here. This is purely inference, right? So this should be faster than actually training. So you're just evaluating its performance on the distribution D1. Right, so I'm gonna just loop through and check how well does it perform on this distribution. And the idea is basically we're just gonna check, is there one of these many classifiers in my bag whose accuracy is at most a half minus gamma half, meaning I'm a gamma half weak learner. And then I'm just gonna go with one of those as my classifier for boosting. And here you can use just classic uniform convergence bounds because my subsamples are just samples from this distribution D1. So we know if I sample D over gamma squared many samples, then if my error is at most a half minus gamma on the sample, it's at most a half minus gamma half on the original distribution with high probability. So this is just standard classic learning theory results. Okay, so I should just in each of these subsamples, I'll just sample something like D over gamma squared many data points. Then I know that the performance of every single hypothesis, the ones that I train on in particular, its error on the sample is within gamma half of its error on the real distribution D1, and its error on the sample is at most a half minus gamma because it's a weak learner. Right? So this is kind of the main idea. Okay, so this is so far that's simple. So this is my check bag procedure, just loop through all these hypotheses that I pre-trained, and I'm going to find one just using inference. I'm not training anything. I'm just going to find one whose error is at most a half minus gamma half on the full distribution D1. Okay. Then I could do a boosting step. Like in AdaBoost, I increase the weights of the data points that are correctly classified. I decrease the weight of data points that are correctly classified. So increase the ones that are misclassified. Right? That gives me a new distribution D2, like in normal boosting. But the trick or the idea now in this algorithm is that we don't want to do another round of training now. We would like to reuse this bag that we already have of pre-trained classifiers. So what I'm going to do now is I'm going to check the bag H1 using the distribution D2. So I'm going to look for a hypothesis in H1 or classifier in H1 whose error is at most a half minus gamma half on the distribution D2. But the difficult part is that H1, this bag that I have, it contains weak hypotheses or classifiers that were trained on subsamples from distribution D1. But now I'm hoping that it still works. It's a gamma half weak learner on the distribution D2. Right? So somehow I sampled from the wrong distribution. Right? I sampled from distribution D1, and I wanted to hope that still the classifier I got works on the distribution D2. So the question is really, when is this the case, right? Is there any chance that the performance on D1 generalized to the performance on D2, right? So is the error here going to be close or not, right? That's the tricky part to argue. So the main algorithm now with this in mind, our algorithmic sketch is as follows, right? So we get our training data set in, I got my weak learner, we're going to start with a uniform distribution over the training samples like AdaBoost does. And now we're going to do these P rounds. And in every round, we're going to do this kind of bagging step. So we're going to construct a bag full of classifiers or weak hypotheses. By doing in parallel, we're going to train T of them in parallel. Each of those we're going to sample from the current distribution, right? So the current distribution is, well, we're going to have a parameter R that allows us to skip several rounds. So we have some distribution now. It's just the one denoted here by D sub P minus 1R plus 1. So that's kind of the current distribution. So we're just going to sample from this current distribution and train a classifier on the subsample. And we're going to do this T times in parallel. So we're just going to draw all these random samples, train on all of them, put all of these classifiers in a bag. And now we're hoping, and this is, here there's no training, so that's important here. Now we're hoping that we can use this bag to perform R steps of AdaBoost, really. So for R steps, we're not going to train a classifier, but we're going to hope that this bag that we have, that this bag contains a classifier whose error is at most a half minus gamma half on a distribution that we kind of have now. And the interesting thing here is that we're going to update these. We're going to do exactly like in AdaBoost. We're going to find one of these classifiers whose error is at most a half minus gamma half. We're going to update the distribution, And then we're going to look again in the same bag. We're not going to do more training. We're going to look in the same bag for hypotheses with errors at most a half minus gamma half on this new distribution. And the hope is that we can kind of repeat this for our steps. So we're not doing any training for our rounds. And still we're making progress in the same sense that AdaBoost would make progress. So that's the main idea. Okay. And again, we're only using inference here. We're only evaluating the performance of our classifiers on the training data set. Okay. Actually, even if one is interested and you want to speed this up, you don't actually have to compute the error exactly on the whole data set. You could also just use a test set, so kind of subsample from the current weighing and test the performance on the subsample. So this actually can also be made fairly efficient. Okay, so this is kind of, so these are, we're hoping to skip our steps here. We're not going to do any training for our rounds. Okay. At the end of the day, we're just going to do some majority aggregation of all these hypotheses that we picked out in every round. Right, so this is exactly the same as AdaBoost, right? So note here, we're training T classifiers hypotheses in every round. We're not going to use all of them. We're only going to use P times R many classifiers, like normal AdaBoost. We're basically just going to pick out one every time. So we're just training all these candidate hypotheses in parallel, and then we're going to find some of them that works. It has this error of at most a half minus gamma half. That's the main idea. Okay, so that's the kind of the full algorithm. It has these P rounds where you in parallel train T classifiers, put them in a bag, and we're hoping that these T classifiers are enough that we can use one of them in the next R steps of boosting, like AdaBoost. Okay, so the kind of proof strategy, the main challenges is that, of course, in every of these bags that we have in these P rounds, the classifiers hypotheses in there are trained on samples from distribution d p minus 1r plus 1, so kind of like the first distribution in this kind of round of R consecutive distributions. So maybe just for a simplifying notation, let's just kind of call it D1 instead, right? So we have a bag trained on distribution D1. And now it's easy. We already argued that you can definitely find a classifier in H1 that's good for the first distribution for D1, right? Because these are samples from the correct distribution. So this is going to work with high probability. The trick is, so the problem is that we're going to update the distribution depending on H, but we're not training again. We keep the bag. The bag was trained on samples from D1, but now we have a distribution D2. So what we really argue here is the way that we try to analyze it and show that one of these hypotheses or classifiers is going to work with high probability is that we basically, the main ingredient is to keep track of the KL divergence between distribution 1 and one of these later distributions, dr, that you see in these R steps that you're doing. And it's not just as easy as looking at the KL divergence. It actually turns out that you have to consider several different cases here to argue that there's always going to be one of these classifiers whose accuracy or error is at most a half minus gamma half. The analysis splits into three interesting cases. One of them is there's a small KL divergence between these two distributions. It makes sense here that since the two distributions look alike, this should be a reasonable chance that one of these random samples is also going to be good on the dr if it's good on the d1, right? So this is kind of like the easy case because our distribution dr looks like d1. So then we're going to be likely to find a good hypothesis as long as this t, the number of things we train on these subsamples, is big enough. Now, the interesting case is it could also happen that the KL divergence between the two distributions is very large. Okay, so this can happen. And here might be hard to find a good hypothesis in the set. But what we kind of show is that it could actually be the case that that what happened is that one of these hypotheses that we already used in one of these steps, since we were at distribution D1, we kind of did some steps. What we show is that it could be the case when the KL divergence is large, it could be the case that one of these hypotheses that we already used, or classifiers that we already used, is so bad on the distribution dr that we can use its negation. So that means that its error is like a half plus gamma half. So it's wrong way more than half the time. Then I can just flip it and do the inverse prediction. So this is something we show that this might also happen. And finally, if this does not happen and we still have large divergence between these two distributions, then we can argue that in some sense we have made a lot of progress in these steps that we've done in this kind of batch of our rounds. We made so much progress that we don't have to do anything more. So maybe if you are aware of the analysis of AdaBoost, classic AdaBoost, what you do there is you look at some kind of exponential loss and then you argue this goes down very fast. Basically, the key in our analysis is to show that if you have large divergence and you cannot use the negation of a previous hypothesis, then this exponential loss has decreased so much as if you already did R steps. So then you can just don't do anything more. That's kind of this last condition. And we need all these three cases, it turns out, to get this optimal behavior. Okay, so maybe just summarize what are then the bounds and results that we get. So recall again, right, the T is the number of parallel calls to a weak learner. R is the number of steps that we want to kind of skip over without training, and P is the number of iteration. P is the actual number of rounds of training in parallel. So what we show is that you can specify an R, so basically how big a factor do I want to decrease the number of rounds by. So then we show with high probability, our algorithm is going to perform well, meaning its generalization error is no worse than AdaBoost. And the number of rounds P is going to be basically what AdaBoost is, log S, which is log M, over gamma squared. And then you also get to divide by this factor R, right? So you shave a factor R in the runtime. The number of things you have to train in parallel is exponential in D times R. Interesting fact is, just if you don't remember the previous bound that we're competing with, to shave a factor R in the runtime, you had to pay exponential in dr squared. So we turn it into dr instead. And then we prove lower bounds, basically showing up to logarithmic factors, not even logarithmic factors in the exponent, but multiplicative logarithmic factors. You show matching lower bounds for all values of R. There's some small caveats here. You should read the paper to see. But basically, this is the main contribution, that this is the right trade-off for parallelizing boosting. Right? So thanks a lot for listening. I hope you enjoyed it.